Our goal in this video is to figure out how to take derivatives of exponential functions and log functions that have bases other than e. So to start off, we're just going to do a little review of some of the rules we have for log functions. Some are going to be a little bit more familiar than others. For example, we use this a ton in pre-calculus, just how we go back and forth between log functions and exponential functions. We did change of base a decent amount there. These rules we did cover, but a lot of them maybe didn't spend a ton of time on. So just kind of glance through them, and we're going to use them in at least one example in this section of notes. Okay, example 7 says use the properties of logs to rewrite the function right here, and then take the derivative of it. Because right now our derivative does not have a base of e, or our log function does not have a base of e. So to start out, I'm going to use a change of base formula. So our change of base formula says that we can pick whatever base we want for the log function. The square root of x, that part will go on top of the fraction that we're going to make, and the 5 will go on the bottom. Here's what I mean by that. We pick a base of e, that's what natural log is, and with square root of x is on top, 5 is on bottom. That's our change of base formula in the top right corner there. Okay, from there, I'm just going to do a couple minor changes. Natural log of 5, you can actually type that into your calculator and it will give you a number answer. So instead of dividing by natural log of 5, I'm going to bring that out to the front and pretend that I'm multiplying by 1 over natural log of 5. That's just a number. Think of that as a coefficient. Actually, I'm a step ahead of myself here, so I'm going to... There we are, we erased that. First thing I'm going to do actually is take the square root of x part and instead of saying square root of x, we're going to raise it x to the 1/2 power. And now I'm going to think of natural log of 5 just being a number. It's going to come out to the front as a coefficient. And then I'm going to use the rule that I have right here that says if I have a power there, the power can come down to the front. So see how the power of k is now down in the front. So the power of 1/2 is going to come down to the front and be multiplying. So times 1/2, and then times natural log of x. And now it's written in a form that I could go ahead and find the derivative of y. Okay, keep in mind, this is a number, that's a number. They are coefficients. So I don't need to worry about them. Our coefficients, we always say, keep them out in the front. Just take the derivative of the actual function, and we know that the derivative of natural log of x is just 1 over x. So in the end, our answer would be 1 over, and then just to kind of combine those two fractions, I'll put the 2 out front times natural log of 5. And then if you want to, you can do it separately, times a 1 over x. You could put the x in that denominator, the first denominator if you wanted to, but this would be the derivative that we're looking for. Okay, this next question is probably much more complicated than you would typically see in a homework question. So don't worry so much about that, but I do want you to get the general technique when they say use log differentiation to find the derivative. Basically what that means is always start by finding the taking the natural log of both sides and then figuring out how you can take the derivative of both sides from there. Usually there's a reason why they're telling you to do that. So I'm going to write down a bunch of stuff for you. This part right here is what I just talked about, how we want to take the natural log of both sides when they say use this technique. Now if you go back up to the original, technically we could go through the quotient rule and the product rule and the chain rule, and we could come up with a derivative for this. It would be very long and messy, and really this method's going to be long and messy too, but we could do it another way. But a lot of times when they say do it this way, it's because algebraically that's probably the only way you can do it, and they're trying to give you a hint on how to get started. And then this line right here, I haven't changed the natural log of y, but what I've done is used a lot of the rules from that box to rewrite things. So we have a rule that says if I'm multiplying two chunks together and I'm taking the natural log of that, I can take the natural log of them separately and they're added together. And if I do division, then I take them separately and I'm doing subtraction. And then this 1/2, that's like saying the square root symbol right up here is the power of 1/2. It can come down to the front using the power rule for log functions. Same thing with the 2/3 there, it's now down in the front. So that's using a lot of those rules from pre-calculus. This is the part that you should not expect to see very much. But I think it's good for you to see this step, and it's good for you to see the rest of this problem worked out. Okay, now after that, we need to take we need to take the derivative of all of these parts. So the derivative of natural log of y is going to be 1 over y. Keep a pen there, 1 over y. And because it involved y's, we're going to have dy dx at the end. Okay, the derivative of the natural log of x is just 1 over x. Derivative of the next part would be, we can keep the 1/2 in front, and then we're going to have times a 1 over x squared plus 1, and then don't forget the chain rule, right? There's a function inside natural log, so the derivative of the inside part is 2x minus, the 2/3 can stay right there. Derivative of natural log is 1 over x. We have a x plus 1 inside instead. And then for the chain rule, I could say I'm going to multiply by a 1 at the end if that just kind of helps you keep track of things. Okay, where do we go from there? A couple things. I can simplify some of these fraction parts in here, so I'll do that at the same time. But also, I'm trying to solve for dy dx, and so I need to get rid of this, so I'm going to multiply by y on both sides. So as I go through all of this, I'm going to say that dy dx is going to equal, and I'll put this in a big parenthesis here, we're going to have 1 over x plus, if I simplify the next fraction, I'd end up with x over x squared plus 1. The third fraction would be a 2 over, and then 3 times x minus 1, plus 1. At least that's one way of writing it. And then remember that we multiplied by y on both sides here, so that now that 1 over y is gone. So I put a y right there. That is an acceptable answer. If they said write it only in terms of x, remember that we know what y equals. Y equals all this stuff up here. So as one additional step, I could rewrite everything in that last line again, except when I got to here, instead of writing a y, I'd write the original function. And sometimes they might expect you to do that, so beware of that as well. In our next two examples, we're looking at what happens with exponential functions that have bases other than e, and we're going to use the idea of logarithmic differentiation to help us out here. We're going to be looking for a pattern that's going to help us find the general rule. So if I'm going to find the derivative of y equals 2 to the x, I already told you that we're going to start by doing logarithmic differentiation. That means take the natural log of both sides when I do that, one reason I do that is because I can bring that power of x down to the front. Oops. Let's erase that a second, because it should be natural log of 2. Okay, and now we're going to take the derivative of both sides. So just a little note that we are deriving at this point. The derivative of natural log of y is 1 over y, and then we need to add the dy dx for implicit differentiation. This next part's a little bit trickier, not really tricky, but remember, natural log of 2, you can plug that into a calculator, you get a number. This is like our coefficient. Ideally, I'd write it out in the front just so we get the idea that it is a number. So all I need to do is find the derivative of x and multiply by the natural log of 2. Well, derivative of x is 1. So on this other side, I just have natural log of 2. And then if I want to, I can say times a 1, just so remember that we took the derivative. Okay, let's solve for dy dx. So dy dx is going to equal natural log of 2 times y. And just like I told you on that previous difficult example, I know what y is. Y is 2 to the x. So in the end, dy dx is going to equal natural log of 2 times 2 to the x. Okay, let's see what happens when I come up with the derivative of 3 to the x in the next example. We're going to start by setting it up the same way. We're going to have natural log of y equals natural log of 3 to the x. And if you take a careful look, the work is going to look oddly familiar, and hopefully you're seeing a pattern in this. If we're going to take the derivative of an exponential function but doesn't have e as the base, basically it comes down to it's going to be the same function, but then you just multiply by the natural log of the original base. And so that's not too hard to remember, but again, when the chain rule comes into play, it gets a little bit more tricky. So this slide just starts off by saying here is another rule that we have. We just went through 2 examples of that, and now we're just going to have several, just a final example where we practice a lot of this stuff from the entire section. So we're taking the derivative of e to the 5x power plus 7 to the x power plus natural log of x cubed plus 4. Let's do a lot of our derivative rules here. So we're going to start off by looking at g prime of x. The derivative of e to the 5x power, derivative of e to the x is itself, so we say e to the 5x. Use the chain rule, we get times of 5. We just went over a rule like this. The derivative of 7x will be natural log of 7 times 7 to the x power. And the derivative of natural log of x cubed plus 4, we'd say that the derivative of natural log is 1 over x. So in this case it'd be 1 over x cubed plus 4. And then we need to finish off the chain rule. Derivative of x cubed plus 4 is just 3x squared. Okay, we might simplify this a little bit, just put it in proper notation. So for the first part I have 5 times e to the 5x power. The next chunk we'd probably just leave the same way, natural log of 7 times 7 to the x power. And the last chunk would be, we'll just write it as 3x squared over x cubed plus 4. Final answer. Hey, we've just conquered chapter 3. Think of any questions you might have and come to class ready to go over some review stuff.